Let's solve a rather interesting thermodynamic problem involving a two-component system. And in this system, one component will be cooled while the other component is heated. And we will see how entropy flows between these two components. A 33.8 pound mass aluminum bar, initially at 200 degrees Fahrenheit, is placed in a tank together with 249 pound mass of liquid water, initially at 70 degrees Fahrenheit, and allowed to achieve thermal equilibrium. The aluminum bar and water can be modeled as incompressible with specific heats 0.216 BTUs per pound mass R and 0.998 BTUs per pound mass R, respectively. For the aluminum bar and water as the system, determine A, the final temperature in degrees Fahrenheit, and B, the amount of entropy produced within the tank in BTUs degree R. Ignore heat transfer between the system and its surroundings. So here's the schematic of our system. We have a tank, and inside the tank is water and a metal bar, an aluminum bar. And I'm going to draw our system boundary around the two. So our system is a two-component system consisting of the metal bar and the water. And the tank is insulated. And so there's no heat transfer from our system to the surroundings outside the tank. Let's look at what we know about our system. The aluminum has an initial temperature of 200 degrees Fahrenheit, which is 660 degrees R. It has a specific heat of 0.216 BTUs per pound mass R, and it has a mass of 33.8 pound mass. The water has an initial temperature of 70 degrees Fahrenheit, which is 530 degrees R, and a specific heat of 0.998 BTUs per pound mass R. The mass of the water in the system is 249 pound mass. We're going to model this as a closed system. Here's our system boundary, and of course there's no mass flowing across the system, so that makes it closed. We're going to ignore any changes in kinetic and potential energy as being completely insignificant, so we'll call those zero. Because the tank is insulated, Q is zero. Remember, there may be heat transfer between the bar and the water, but that takes place inside our system. There is no heat transfer between the system and the surroundings, so Q is zero. And there's no mechanism on this tank for doing work, so work is zero. So what we have here is what's known as an isolated system. An isolated system exchanges absolutely nothing with its surroundings. There's no mass transfer from the system to its surroundings, no heat transfer from the system to the surroundings, no work transfers energy from the system to the surroundings. And so an isolated system is often thought of as its own little universe because it doesn't interact with the surroundings in any way. Now inside our system are this metal bar and water. Both are incompressible materials, and both have a constant specific heat. We want to find the final temperature of the system and the entropy produced in the system by this process. Let's solve for the final temperature by writing an energy balance. When we have a closed system and are ignoring kinetic and potential energy, we can write that delta U is Q minus W. Yeah, but we had said that Q is zero and W is zero, so delta U must also be zero. But what is delta U? We have two components. So we can say that delta U for the system is delta U for the aluminum plus delta U for the water. And whenever we're dealing with solid components or incompressible components, we can write that delta U is the mass times the specific heat times the change in temperature. So let's substitute this expression in our delta U equation. So we have delta U for the system is delta U for the aluminum. Well, that's going to be the mass of the aluminum times the specific heat for the aluminum times the final system temperature minus the initial aluminum temperature, plus delta U for the water, which is going to be the mass of the water times the specific heat of the water times T2 minus the initial temperature of the water. And that whole expression is going to equal to 0 because we have delta U is equal to 0. Now let's rearrange this expression and solve for T2. Well, T2 is the mass times specific heat times initial temperature of the aluminum plus the mass times the specific heat times the initial temperature of the water divided by the mass times specific heat of the aluminum plus the mass times specific heat of the water. Now we have all of these values and we can plug them all into this equation, run them through our calculator, and we get the final temperature is 533.7 degrees R, which is 73.7 degrees Fahrenheit. Recall that the initial water temperature was 70 degrees Fahrenheit. So in cooling the aluminum bar, we have raised the temperature of the water by 3.7 degrees Fahrenheit. Now we want to calculate the entropy that was produced inside the system during this process. And again, we have a two-component system, so delta S for the system is delta S for the aluminum plus delta S for the water. And the change in entropy for any system is given by the entropy transferred into the system by heat transfer, which is this integral of dq over T, plus sigma, which is the entropy produced within the system. Now Q is 0, so this whole integral is 0, leaving us with the entropy production inside this system during this process. It's just delta S for the aluminum plus delta S for the water. Now we're going to introduce a new equation here. When we have incompressible materials, we can say that the change in entropy during a process is the mass times the specific heat times the natural log of T2 over T1. So let's plug this new expression into this equation we have for entropy production. We have the entropy production is delta S for the aluminum. So sigma is equal to mass times specific heat for the aluminum times the natural log of T2 over T1 for the aluminum. And sigma also includes this term delta S for the water. So that's going to be plus the mass of the water times the specific heat of the water times the natural log of T2 over T1 for the water. So delta for the system can then be, we can substitute values for all of these variables in this expression. And we'll get one step away from a solution here. And we can say that delta S for the system is delta S for the aluminum plus delta S for the water, where delta S for the aluminum is minus 1.5507 BTUs degree R, and delta S for the water is 1.7288 BTUs per degree R. Now we add this together and we get that the entropy produced by the system during this process is a positive 0.1781 BTUs per degree R. Now note that delta S for the aluminum is negative and delta S for the water is positive and delta S for the system is positive. Let's explore that a little bit. Let's note the following. The entropy of the aluminum decreased during the process. Remember that heat transfer removed energy from the aluminum, and entropy flows with heat transfer and in the same direction. Now the entropy of the water, on the other hand, increased during the process. Again, heat transfer added energy to the water, and entropy flows with heat transfer in the same direction. Now the entropy increase of the water was greater than the entropy loss of the aluminum, resulting in the entropy production for the system being positive, which it must be for any real process to take place. And we know that this is a real process. It's obvious just from our experience that we put a hot aluminum bar into a tank of colder water. The heat transfer will occur from the hot bar to the cold water. So we expect to get a positive entropy production for this system. What created the entropy? Well, entropy in the system is largely created by spontaneous heat transfer from the hot aluminum to the colder water. heat transfer always being an irreversible process.